Welcome back to the deep dive. Today, we are moving beyond the messy, continuous flow of classical fluid dynamics. The streams and the turbulence we've often discussed.
We're stepping into the extremely elegant world of wave mechanics.
And our entire mission today is really centered on energy transport. We're looking at how a physical disturbance can travel, sometimes for vast distances, without actually moving the matter it's traveling through.
That is the crucial distinction, right? We're setting aside the whole concept of a water molecule moving permanently from point A to point B.
Yeah, that's not what's happening.
Instead, we're focusing on how let's say, the information or the energy of that initial disturbance gets handed off sequentially down a chain of molecules.
The sources you provided give us a beautifully rigorous path for this. We start with the core math that governs all waves, and, well, it takes us right up to the spectacular pressure physics of a sonic boom.
It does indeed.
Okay, let's unpack this right at the start, because this is the fundamental aha moment that opens up the whole topic.
Yeah.
If you're trying to grasp the core concept, we have to define the precise difference between a simple, localized movement and a fully propagating wave.
It really boils down to dimensions of periodicity.
Okay.
You have an oscillation of vibration. This is a phenomenon that is periodic in time only. So if you watch a single point, say a simple pendulum swinging back and forth, its position repeats over a fixed time period.
That's just a localized rhythm.
Exactly. It's all about what's happening at that one single point.
But a wave is different.
A wave, however, is a collective phenomenon. It has to be periodic in time and periodic in space. It is a disturbance, an oscillation that is propagating or traveling.
Like a ripple moving across a pond.
Perfect example. The water surface bobs up and down, that's periodic in time, but the crest itself is moving across the surface, which is periodic in space.
So the disturbance travels, but the water itself doesn't really go anywhere.
Precisely. The water molecules just move locally up and down or back and forth around a fixed equilibrium point. And crucially, there is zero permanent material transport in an ideal wave.
That makes our deep dive very clear. We need to first understand the fundamental mathematical law, the wave equation, that forces this elegant coupling between time and space.
Right. Then we can apply it.
Then we apply it to sound, look at how the energy is measured using the logarithmic decibel scale, and then explore what happens when waves interact.
Interference, reflection, all the good stuff.
Exactly.
So to start decoding the mechanics, we begin with the simplest mathematical guess for what a smooth, traveling wave must look like. We call it the harmonic wave and sets.
This is the classic sine function that describes cyclical movement, right? But now we have two variables, time and position, operating simultaneously inside that function.
Precisely. Let's look at the structure. Inside the sine function, you have two terms, an omega t term and a nx term. The first one, involving the angular frequency omega, defines the temporal periodicity.
The rhythm.
The rhythm, yes. If you freeze the location, say at x equals 0, and just watch the displacement over time, the time period tolerance is just 2 pi over omega.
And the second term, the one with the wave number dollars, that must define the spatial periodicity. If you freeze time and take a snapshot of the wave.
You see the wave repeat itself in space. That repeating distance is the wavelength, lambda. And just like omega defines the frequency of the oscillation, the wave number, K-list defines the frequency of the spatial pattern.
So $10 is 2 pi over lambda. It tells you how quickly the phase is changing with distance.
You need both of those parts to properly define a traveling wave.
Okay, so we have the math to describe the wave, but the most important physical descriptor is its speed. How fast is this disturbance, this crest or trough, actually traveling through space?
We define the phase velocity, $, by tracking a single point on the wave, let's say a crest. Mathematically, that means we're moving in time $2 in space such a way that the phase, the argument inside the sine function, remains constant.
So you just set the inside of the sine function to a constant, let's say 0. So omega t minus kx equals 0.
And that gives you a beautiful relationship.
It does. If omega t equals kx, then the speed, which is distance over time, $6 over $2, must be the ratio of the two constants, omega over k. So the phase velocity equals omega over k.
And this simple ratio links the two types of periodicity. If you know the temporal rhythm and the spatial rhythm, you automatically know the speed at which the disturbance is propagating.
Now here is where the deeper physics emerges. This harmonic function isn't just a convenient description, it's the specific solution to a universal law of mechanics.
The wave equation.
The wave equation.
Yeah.
And the sources show us we can prove this just by taking derivatives.
We're essentially stress testing our guess to see what underlying rule it must obey. And it turns out that for any function that describes a traveling wave, there has to be a fundamental relationship between how it changes in time and how it changes in space.
Let's maybe skip the nitty-gritty of the partial differentiation, but talk about the result. We know that the acceleration of any tiny piece of the medium is the second time derivative.
Right. And we also know that the second spatial derivative describes the wave's curvature.
So what happens when you do that?
Well, when you perform the two-time derivatives on our harmonic wave function, you get the original function back, but it's multiplied by a factor of minus omega squared.
Okay.
And when you perform the two spatial derivatives, you also get the original function back, but this time it's multiplied by a factor of minus k squared.
So the acceleration, the second time derivative, is proportional to the curvature, the second spatial derivative.
Exactly. And the proportionality factor, if you just divide one by the other, is omega squared divided by k squared, which is just
V squared, the speed squared.
This is the magnificent result. The acceleration of any piece of the medium must be equal to the speed of the wave squared, multiplied by the curvature of the medium at that point.
Which gives us the wave equation. The second derivative with respect to time equals v squared times the second derivative with respect to space.
And that single equation governs waves on a string, sound in air, and even light in a vacuum. It's incredibly powerful.
It is, but we need to dive deeper into the physical meaning of that equation, especially that second spatial derivative, the curvature term. This is where we connect the abstract calculus back to Newton's second law.
Right, we're bridging math and mechanics. Newton says force equals mass times acceleration. The second time derivative is the acceleration. So the left side of our wave equation is essentially acceleration.
Which means the right side must be proportional to the force causing that acceleration.
And the right side contains the curvature term. Let's use the source's excellent analogy. Imagine a chain of masses connected by tiny ideal springs.
Okay, little beaded chain.
If you displace one of those masses upwards, the spring tension from the left and the spring tension from the right both pull on it. Now, if the chain is perfectly straight, even if it's slanted, meaning the slope is constant, those tensions balance out perfectly.
So no net force.
No net force.
Yeah.
Zero displacement or even a constant slope doesn't cause a movement back toward equilibrium.
A restoring force only comes into play when the chain is curved.
Exactly. If the slope on the left is steeper than the slope on the right, the tension from the steeper side exerts a greater vertical component of force. That creates a net force that pulls the mass back toward equilibrium.
And that difference in slope, the rate at which the slope changes, is precisely what the second spatial derivative measures. It's literally a measure of curvature.
The insight here is profound. Restoring force is proportional to curvature. Because the curvature of the wave determines the net force on any particle, and that net force determines the particle's acceleration, we land exactly back on the wave equation.
So the acceleration of one little piece of mass is directly caused by the curvature created by its neighbors. That's the physical mechanism.
That's how the information gets passed down the line.
And since the wave equation is so robust, it must apply in our three-dimensional world, not just a 1D chain.
Absolutely. When we generalize this, we have to account for curvature in all three spatial directions, x, y, and z.
Or you just add them up.
You add them up. The sum of the 3 second spatial derivatives, the total curvature in 3D space, is collected into a single term. It's known as the Laplace operator, often symbolized as delta.
And that allows the equation to describe plane waves, spherical waves, and any other disturbance propagating through 3D media, like air or water.
That mathematical framework is the bedrock.
Okay, so let's apply it. Let's take this and apply it to the mechanical wave we experience every single day. Sound, which is just a pressure wave traveling through a fluid like air.
To handle sound, we have to start with the governing laws of fluid dynamics, the Euler momentum equation and the continuity mass conservation equation, our old friends.
But those equations are notoriously complex and nonlinear. They're incredibly difficult to solve directly.
Which is why the sources highlight a crucial simplification step, linearization. We treat sound as a tiny, tiny fluctuation superimposed on a vast stationary medium.
This is absolutely vital for making the math tractable, isn't it?
It is, because sound waves involve such small amplitudes and small particle velocities, we can just ignore any term in the Euler equation that involves the particle velocity dollar multiplied by itself.
So, like the convective acceleration term is small times small.
It's negligibly small compared to the other forces. We're essentially saying the wave is so tiny we can pretend the medium is standing still except for this little pressure fluctuation.
Okay, that makes sense.
With that linear simplification, we can combine the time derivative of the continuity equation with the linearized Euler equation. The algebra, after you eliminate the velocity component, leads us directly back to
The wave equation.
the wave equation, but now applied to the sound pressure PD. We get that the second time derivative of $t is equal to v_2 times the Laplace operator applied to tail.
And by matching the constants derived from the physics with that v.02 term in the wave equation, we can actually extract the sound speed.
And we get the fundamental result for the speed of sound in any fluid medium. V$ equals the square root of 1 over rho times kappa, density times compressibility.
Okay, that's an elegant formula, but what does it tell you physically? If you're standing outside, how do you know if sound is going to travel fast or slow?
The formula gives us two clear handles: stiffness and heaviness.
Okay.
Speed increases when the medium is stiff, that is, when the compressibility, kappa, is low. It's difficult to squeeze the medium.
And it decreases when the medium is heavy, when the density, rho, is high.
And these two factors are constantly fighting each other, as the examples in the sources show.
Right. Take air. Sound travels at about 343 meters per second.
Now compare that to water. Water is far, far denser, much higher rho, which should slow the sound down. But water is also vastly more incompressible. Its kappa is tiny, the stiffness completely dominates the heaviness, and the speed jumps to almost 1,500 meters per second.
Now let's look at the classic case, helium. It has a similar compressibility to air, but its density is incredibly low.
And since density is in the denominator, the speed just rockets up to over 1,000 meters per second, nearly triple that of air.
Which leads directly to the famous Mickey Mouse voice effect.
Exactly. And this is a great aha moment that clears up a common misconception.
Right. You aren't vibrating your vocal cords 3 times faster when you inhale helium.
Not at all. The fundamental frequency of your voice, set by your vocal cords, remains completely unchanged.
So what's happening?
The much higher speed of sound inside the helium-filled air column of your mouth and throat shifts all the resonant frequencies upward. The standing wave patterns that amplify and shape your voice all shift to higher frequencies.
So you're hearing the same fundamental tone, but the harmonic overtones that define the timbre are all altered,
making the pitch sound much higher. It's a textbook case of how sound speed changes acoustic perception.
That covers fluids in general. But gases, like air, have an added layer of complexity when we calculate that crucial compressibility term.
They do. It's because we have to consider the speed of the wave itself. When you compress a gas slowly, an isothermal process, the heat generated by the compression has time to dissipate into the environment.
So the temperature stays constant, and the simple ideal gas law, P times V is constant, applies.
But sound waves are fast, 343 meters per second fast. The pressure changes happen almost instantaneously.
No time for heat to escape.
Correct. The compression zones heat up and the rarefaction zones cool down. But heat doesn't have time to equalize across the wavefront. This makes sound propagation an adiabatic process. No net heat is exchanged.
And the adiabatic condition introduces the adiabatic exponent, gamma, into the equation.
Yes. When we derive the compressibility based on the adiabatic condition, that gamma factor gets inserted directly into our sound speed formula for gases. It gives us $5 equals the square root of gamma times P over rho.
And gamma depends on the molecular structure of the gas.
Precisely. Simple monatomic gases like helium are rigid, so gamma is 5/3. Diatomic gases like air, nitrogen, and oxygen have a gamma of 7/5.
And that difference matters because complex molecules have, internal degrees of freedom, ways they can rotate or vibrate.
That's the physics. When the wave compresses the air, some of that compression energy gets hidden, you could say, in those internal rotational or vibrational modes. It doesn't all contribute to the pressure change.
So by soaking up some energy internally, the gas appears slightly less stiff.
Which means gamma is slightly lower, and consequently, the sound speed in diatomic air is a tiny bit slower than it would be in a theoretically rigid gas of the same density.
Now for the critical real-world question. If pressure is in the speed formula, why doesn't sound travel dramatically slower on a mountaintop where the atmospheric pressure is so much lower?
Because pressure and density are linked through the ideal gas law. If you reduce the pressure in a system while holding the temperature constant, the density drops proportionally.
So the ratio P over rho remains completely stable.
Exactly. So pressure changes alone, like moving up or down in altitude, do not change the speed of sound as long as the temperature is stable.
So if altitude doesn't really matter, what factor reigns supreme in determining the speed of sound in air?
Temperature is king. Temperature T is the only variable that truly changes that crucial P over rho ratio.
How so?
When air warms up, it expands, it becomes less dense, so rho decreases. Since rho is in the denominator of our equation, the speed dollar must increase. Mathematically, dollars is proportional to the square root of the absolute temperature.
And this temperature dependence isn't just an abstract formula. It has massive real-world implications, especially in music.
Oh, absolutely. Think about an orchestra tuning up. If the concert hall starts cold and then warms up significantly from the audience and stage lights.
The speed of sound increases inside all the wind and brass instruments.
Flutes, clarinets, organs, all of them. Because the resonant frequencies of those instruments depend directly on the speed of sound inside them, an increase in dollar means all their notes go sharp,
The entire ensemble slowly shifts out of tune.
forcing adjustments throughout the performance. It is a perfect live demonstration of that relationship between velocity and temperature.
This sensitivity of sound speed to temperature leads directly to another fascinating class of phenomena where sound doesn't travel in straight lines but actually bends. Acoustic refraction.
The sources call this the acoustic fata morgana, which I love. It explains the surprising clarity of distant sounds over water, for example.
So let's paint the picture. A warm day over a cold body of water, like a quiet lake.
Right. Normally, air gets colder as you go up, but here the water cools the air right above the surface, creating a temperature inversion. Cold air near the ground, warmer air above it.
And we just established that sound travels slower in cold air and faster in warm air.
So as a wave front travels out over the lake, the upper part of that wave front accelerates in the warmer air, while the lower part in the cold layer slows down.
It's like a marching band trying to cross a field and half the band hits a deep patch of mud.
Perfect analogy.
The side in the mud slows down, forcing the entire marching line to wheel around.
The wave front literally tips over, and the sound ray is continuously bent downward, curving back toward the surface of the lake.
So instead of the acoustic energy just vanishing into the sky,
It's focused and concentrated along the surface, and that's why you can hear a conversation on the far shore that would be completely inaudible if the temperature gradient were reversed. The environment acts as a giant acoustic lens.
and we see an almost identical bending effect caused by wind, which also creates a speed gradient.
Right. Wind speed is basically zero right at the ground due to friction, and it increases dramatically with altitude.
So if you have a tailwind.
The wind speed aloft adds to the sound speed, making the top of the wave travel faster. Just like the temperature inversion, the wave bends downward, focusing distant sounds. You might hear highway traffic much louder than you'd expect.
And conversely, if you have a headwind, the faster wind aloft subtracts more significantly from the sound wave speed.
The top of the wave is slowed down, and the wave is refracted upward into the sky.
This creates a sound shadow on the ground.
Exactly. You could be listening to a band in a field and not hear them clearly, but someone standing on a hill far behind you might hear the sound perfectly because it's curved overhead and come back down.
It's the same physics, just a different cause for the speed differential.
Moving air instead of varying temperature.
Speaking of how waves propagate and interact with objects, this brings us to a foundational concept that explains why sound doesn't just travel in straight lines like simple beams of light. The Huygens principle.
Yes, from the 17th century, Christian Huygens proposed this revolutionary idea. Every single point on a wavefront should be considered the source of a new, small, spherical wave, an elementary wave.
And the new, larger wavefront at a later time is just the envelope, the tangent surface of all those countless tiny elementary waves.
It might sound overly complex, but it perfectly explains diffraction or bending around corners.
Right. If a plane wave hits a wall with a small doorway, a simple ray model would predict a sharp shadow behind the door.
But the tiny points lining the edge of that doorway immediately generate new elementary waves that spread out spherically, filling the space behind the barrier.
And that's why you can hear someone speaking from around a corner in a hallway, even though you can't see them.
The wave is literally rebuilding itself behind the obstacle.
So what happens when a wave encounters a fixed obstacle, like a rigid wall? That's reflection.
Here, we have to apply a specific critical boundary condition. The air particles cannot penetrate the wall.
So their velocity perpendicular to the wall, let's call it AA, has to be exactly zero right at the wall surface.
But the incident wave is continuously carrying energy and momentum toward that wall, trying to force the air molecules to move.
So something has to give.
Since the air cannot move, the pressure must build up to stop the incoming momentum. The only way to satisfy that zero velocity condition is for a reflected wave of equal amplitude to run back, perfectly out of phase with the incident wave's velocity.
So at the wall, the velocities cancel out, but the pressures add up.
Precisely. You get a velocity node, a point of no movement, but a pressure antinode, a point of maximum pressure. The pressure fluctuation right next to a hard wall is actually double the pressure of the incident wave alone.
That's a useful practical insight. If you put a microphone right next to a hard, flat surface, you get what is effectively a +6 decibel increase in pressure.
All due to this immediate constructive interference.
And when waves hit at an angle, the law of reflection is exactly what you'd see in a game of billiards.
It's guaranteed by vector physics. The component of the wave number vector running parallel to the wall is unchanged. The component running perpendicular to the wall must reverse its sign.
And that vector reversal dictates that the angle of incidence must equal the angle of reflection.
The same law for light, sound, everything.
Okay, let's talk about the power of a wave. It's all about transporting energy. If a sound wave is traveling through the air, where exactly is that energy physically stored?
The energy in a mechanical wave exists in two forms that constantly trade places: elastic energy and kinetic energy.
Elastic energy is the potential energy stored in the compression and rarefaction of the medium, right? Like the energy in a compressed spring.
And the kinetic energy is stored in the motion of the air molecules as they oscillate back and forth.
And our sources cite a crucial insight from the equipartition theorem. In a smooth harmonic wave, the average potential energy density and the average kinetic energy density are exactly equal.
This simplifies things greatly. It means the wave is constantly and perfectly swapping energy back and forth between the state of motion and the state of compression.
At maximum compression, all the energy is elastic. A quarter cycle later, it's all kinetic.
Exactly.
We don't generally talk about energy density, though. We talk about intensity, which is the flow of that energy.
Right. Intensity, $, is the measure of energy flowing per second through a surface of 1 square meter. It's measured in watts per square meter, and it's directly related to the total energy density, epsilon, and the speed, $5.
So intensity equals energy density times speed. And since we established that energy density is proportional to the square of the pressure amplitude,
this leads us to the most fundamental power law in acoustics. Intensity is proportional to the square of the pressure amplitude. A $1 is proportional to p Bevel squared.
this is so critical to understand because the relationship between what we measure, which is pressure, and the actual physical power being delivered is highly nonlinear.
If you double the sound pressure, you are actually quadrupling the amount of acoustic power.
Let's put this incredible scale into perspective with real numbers because they are truly staggering. Atmospheric pressure is about 100,000 Pascal. Our sources say that a sound pressure fluctuation of just 1 Pascal corresponds to an intensity of about 1.2 milliwatts per square meter.
And 1 Pascal is already incredibly loud for the human ear. That's a jackhammer or a loud rock concert. It's tiny compared to the atmosphere, but huge for our ears.
And the quietest sound we can possibly detect, the threshold of human hearing, is 20 micropascal. That's 2 times 10 to the minus 5 Pascal.
So the dynamic range of our hearing, from the quietest whisper to the level that causes physical pain, spans over a factor of 10 million in pressure.
Trying to plot that on a linear scale of pascals is just impossible. The quiet sounds would vanish, and the loud ones would fly off the chart.
Which is the sole powerful reason why the decibel scale exists. It is a logarithmic scale designed to compress that immense dynamic range into manageable numbers.
We define the sound pressure level, L+, using the formula. 20 times the log base 10 of the measured pressure divided by a reference pressure.
And that reference pressure is standardized to 20 micropascals, the average threshold of human hearing at 1 kilohertz.
This means 0 decibels is not absolute silence. It is the reference point, the quietest sound the average ear can detect.
Now, for the common point of confusion you identified, why is the multiplier 20 for pressure but only 10 for intensity?
Right, the sound intensity level, log dollars, is defined as 10 times the log of intensity over reference intensity.
It's an elegant mathematical solution to a physical problem. We know that intensity, $1, is proportional to pressure squared.
So if you substitute that into the intensity formula,
you get that the louder $, is proportional to 10 times the log of p squared. And because of the fundamental rule of logarithms, the exponent of 2 just moves to the front.
So 10 times log p squared becomes 2 times 10 times log p, which is 20 times log p.
The scale is designed so that the numerical value of the sound pressure level is always identical to the numerical value of the sound intensity level. It ensures consistency.
And the consequence of this design is that if a sound increases by 20 decibels, the actual pressure fluctuation has only increased by a factor of 10.
But the physical intensity, the power, has increased by a factor of 100.
Let's use the benchmarks. Normal conversation is around 60 dB. The pain threshold is 120 dB.
That difference of 60 decibels is 3 factors of 20, meaning the pressure difference is 10 times 10 times 10 or 1,000 times higher, and the intensity is 1,000,000 times higher.
The handy rules of thumb for listeners to internalize are: a plus 6 dB increase means you've doubled the sound pressure.
And a plus 10 dB increase is what the human ear generally perceives as a doubling of subjective loudness.
We've spent a lot of time on the ideal plane wave, but in reality, most sound sources, a person speaking, a trumpet, are point sources, radiating energy spherically outward.
This means the wave crests are spheres and the energy spreads out as the wave travels. This changes the amplitude calculation completely, but it must still obey the law of conservation of energy.
Right, the total power radiated by the source has to remain constant, ignoring friction.
And if that constant power spreads over an ever-increasing spherical surface area, which is 4 pi r squared, the intensity must necessarily decrease.
This forces the crucial inverse square law. Intensity, which is power divided by area, must decrease with the square of the distance.
And since we know intensity is proportional to the square of the pressure amplitude, this means that the pressure amplitude itself must decrease linearly with distance.
So total dollars is proportional to 1 over $3. The spherical wave equation has to include a term that scales down the amplitude as it travels.
That division by $3 ensures energy is conserved. And this linear decay of amplitude with distance is why speech comprehension just falls off a cliff after a few meters.
Right. If you move from 1 meter to 10 meters away from a speaker, the amplitude is dropped to 1/10.
And the intensity, the actual power reaching your ear, has dropped to 1/100th.
We can translate that back to the decibel scale. Since doubling the distance reduces the intensity to 1/4, and 10 times the log of 1/4 is about minus 6 dB.
We get a powerful rule. Every time you double the distance from a point source, the sound level drops by 6 decibels.
And when you realize how little energy is involved, a normal conversation emits only about 25 microwatts of acoustic power.
The inverse square law explains why our incredibly sensitive ears still struggle so much with distant sounds.
Let's shift now to what happens when 2 or more waves occupy the same space at the same time. This is governed by the superposition principle.
The mathematical foundation is robust. The wave equation is linear. If we have 2 solutions, P11 and P$2's, their sum, P$ plus P$, is automatically also a solution.
Physically, this means waves pass right through each other completely undisturbed.
Like 2 pebbles in a pond, or the fact that your phone, Wi-Fi, and radio signals are all traveling through the air right now without crashing into each other.
They just add up linearly at the receiving end.
The only real-world limitation is that this only holds for small amplitudes. Extremely high intensities can cause nonlinear effects, but for most acoustic waves, superposition is king.
And the observable consequence of superposition is interference.
Yes, interference is just the result of the addition. If 2 wave crests meet, they add up to create a supercrest. That's constructive interference.
If a crest meets a trough, they cancel each other out, potentially resulting in silence. That's destructive interference.
And for us to see a stable interference pattern, a fixed region of silence next to a fixed region of loudness, the sources have to meet a special requirement.
They must be coherent.
Coherence is essential. It means 2 things. They must be oscillating at the same frequency, and critically, they must maintain a fixed, predictable phase relationship. They have to be oscillating in sync.
If they weren't, the interference pattern would just smear out into uniform noise over time.
Exactly. The sources make a useful distinction here between spatial and temporal coherence.
Right. Spatial coherence is about the size of the region where the phase relationship holds.
And temporal coherence is about how long the source maintains a single, stable sine wave. A laser has excellent temporal coherence. A light bulb has terrible temporal coherence.
When interference reaches its most dramatic stationary result, we get the standing wave.
A standing wave is simply the result of an incident wave interfering with its own reflection, usually trapped in a confined space like a guitar string or an organ pipe.
When the waves are running in opposite directions, they create fixed points in space. These nodes are the points where the waves always cancel out.
Zero movement or zero pressure. And conversely, the antinodes are the fixed points where maximum constructive interference occurs. The medium at these points oscillates wildly.
And the key physical insight here is that while the medium is moving vigorously, a standing wave transports no net energy in the direction of the wave.
The energy is just sloshing back and forth between the nodes. The math confirms this beautifully. When you add the incident and reflected waves, the resulting equation separates the variables.
Instead of a single term combining time and position, you get a product of two functions, one depending purely on time and one depending purely on position.
That separation of time and position is the mathematical signature of a standing wave. The position term sets the fixed spatial pattern, the nodes and antinodes. The time term just dictates that the amplitude at those fixed points oscillates up and down.
The pattern itself is frozen in space, and this is the basis of resonance.
In any confined system, only those specific frequencies, the natural frequencies that result in a stable standing wave, can exist. Everything else dies out.
So far, we focused heavily on sound in gases, which are longitudinal waves.
In a longitudinal wave, the oscillation of the particles is parallel to the direction of wave propagation, just compression and dilation.
But there are also transverse waves, where the oscillation is perpendicular to the direction of propagation, like a ripple on a string, or light itself.
Even on a simple string, the physics is governed by the wave equation. The restoring force is still proportional to the curvature. But in this case, the speed depends on the tension and the mass per unit length.
So the wave equation is universal, but the speed factor, v squared, depends entirely on the specific elastic mechanism of the medium.
And the most important practical difference between these two wave types is polarization.
Right. A transverse wave can be oriented vertically, horizontally, or at any angle. That's polarization.
But for a longitudinal wave, like sound in a gas, the movement is forced along the line of travel, so polarization is physically impossible.
Now let's dive into waves in solids. The sources confirm that solids are unique because they are the only media where both longitudinal and transverse mechanical waves can exist at the same time.
This is because solids resist two types of deformation. A longitudinal wave involves stretching and compression, which is resisted by the material's elasticity modulus, E.
But solids also resist being sheared or twisted, unlike liquids.
And that resistance to shearing drives the transverse wave. It's quantified by the material's shear modulus, G.
And since the moduli are different, solids must have two distinct sound speeds.
Both following the general rule of square root of modulus over density. This is the foundation of seismology. Earthquakes generate two types of body waves. P waves, which are primary and longitudinal, and S waves, which are secondary and transverse.
And the P waves are always faster.
Always. The sources cite aluminum. P waves travel at over 6,000 meters per second, while S waves are much slower at around 3,000.
And this speed differential is how we map the planet. The P waves arrive first at a seismograph, then the S waves. The time difference reveals the distance to the epicenter.
And even more importantly, because liquids have a Shu modulus of 0, S waves cannot travel through them at all.
Which is how we know the Earth's outer core is liquid. The S waves hit it and just stop dead.
That's the proof.
Before leaving standing waves, we have to cover the two-dimensional case, which is perfectly visualized by the Chladni figures.
Ah, yes, Chladni's discovery. On 2D surfaces like metal plates, the fixed points of minimum oscillation, the nodes form intricate symmetrical nodal lines.
If you sprinkle fine sand on the vibrating plate, the sand is thrown off the highly oscillating antinodes and accumulates quietly along those stationary nodal lines,
creating these beautiful, visible geometric patterns. And this isn't just a parlor trick.
No, these patterns correspond to the natural resonant frequencies of the material.
Violin makers still use this principle today to precisely tune the thickness and shape of the wooden plates, ensuring they vibrate at the desired frequencies for optimal sound.
Okay, we've covered static sources. But the physics gets really interesting when the source itself is moving rapidly. That brings us to the Doppler effect.
The familiar change in pitch from an ambulance siren. When it moves toward you, the pitch is higher. When it moves away, the pitch drops.
Physically, the source is moving in the same direction as the wave it creates. It's chasing its own crests.
Ahead of the source, the waves get compressed. This leads to a shorter wavelength and a higher observed frequency or pitch. Behind the source, the waves are stretched out, resulting in a longer wavelength and a lower pitch.
The formula in the sources confirms this. The observed frequency is the emitted frequency divided by 1 minus the ratio of the source speed to the wave speed.
So if the source is moving toward you, the denominator is less than 1, mathematically guaranteeing the observed frequency is higher.
And this is essential in everything from radar guns to astronomy, where the Doppler shift of light tells us how fast galaxies are moving.
It is.
But the Doppler effect assumes the source is slower than the wave speed. What happens when the source velocity equals or exceeds the wave velocity?
That's the transition to supersonic travel, and it results in the dramatic formation of the Mach cone and the sonic boom.
If a jet is flying at the speed of sound, or faster, it's traveling at least as fast as the pressure waves it generates. The waves can't escape ahead of the source.
So the jet is constantly running into and generating new pressure waves. All of those waves pile up violently along a conical surface.
The Mach cone.
This conical region represents the superposition of countless wavefronts, leading to a massive sudden increase in pressure. And this huge pressure shock waves is what we hear on the ground as the sonic boom.
And the geometry of this cone is directly related to the speed of the aircraft via the Mach number, which is just the ratio of the jet speed to the speed of sound.
Right. The opening angle of the cone is defined by the relationship. The sine of the angle equals 1 over the Mach number.
So if a jet is flying at Mach 2, the sine of the angle is 1/2, meaning the cone opens at 30 degrees.
And the faster the jet flies, the higher the Mach number, the sharper and narrower the cone becomes, concentrating that pressure even further.
We've concluded our deep dive into wave mechanics. We started by grounding the entire field in one powerful principle, the wave equation. It demands that the acceleration of any particle must be proportional to the curvature imposed by its neighbors.
And we applied that principle to sound, showing that the physical speed is dictated by the battle between a medium's stiffness and its heaviness. We saw why temperature is the ultimate regulator of sound speed in the atmosphere.
Influencing everything from the tuning of an orchestra to how sound bends across a lake. And finally, we demystified the decibel scale. It exists out of necessity, because the dynamic range of sound intensity is astronomically large.
The core takeaway, I think, is that the behavior of waves, whether it's the stillness of a Chladni figure or the violent pressure front of a Mach cone, is nothing more than the elegant translation of Newton's laws into space and time.
We ended our discussion on P waves and S waves in solids, noting they travel at two different speeds because they are driven by two different material moduli.
That structural complexity isn't just an academic footnote, it defines our planet.
Indeed. So let this be your final provocative thought. The fact that S waves cannot travel through liquids is crucial. Seismologists rely on this to map the Earth's interior. When P waves and S waves encounter the boundary between the solid mantle and the liquid outer core, the P waves bend, but the S waves are completely blocked.
They cast a massive sound shadow on the opposite side of the planet.
So think about how a simple difference in wave type allows us to chart the unseen structure of the world, thousands of kilometers beneath our feet. It's the fundamental tool that proves, beyond a shadow of a doubt, that the heart of our planet is liquid.